Hi, so I'm Dean Freeman. I'm a senior test engineer at NSS Labs. For about the last 6 months before that, I was doing FIPS and Common Criteria validations and consulting, which is what got me looking into this subsystem.
Thanks for the introduction. As I mentioned, I'm Principal Security Architect at New Context. Previously, I was at Cryptography Research, which is actually where I got a lot of my experience and other stuff. So yeah, New Context has been also very useful, and you can also follow me on Twitter at inkthenet. So, you've probably seen a few graphics on exactly what is randomness. This is one of the classic ones. Get random number, return 4, chosen by a fair dice roll, guaranteed to be random. Well, I rolled it, clearly it must be random, so it's good for randomness forever. So the question is, what are the risks of a bad RNG? Because, a lot of people, some people hear about them, but the thing you always hear about is cryptography, symmetric algorithms, public-private key infrastructure, all that other stuff. But you rarely actually hear about an RNG. There are actually real-world impacts if your RNG is bad or has been compromised. One of the other ones was the digital signature schemes. There's a nonce that is used as part of the signature. It is required during all signatures that you ever do during the lifetime of your private key that nonce must never be reused. If it's ever been reused, your private key will leak. Sony, when they were signing binaries for the PS3, there was a mistake made. Nonce was reused, and the signing key for PS3 binaries was leaked, allowing people to hack and be able to load their own binaries on the PS3. Clearly, very bad break. Then there's also the wonderful Debian SSH key issue. They were looking at this code, looked at like they were reading uninitialized variables, removed the code. Turns out it completely broke all of the seeding of the RNG, and there was only 32K different keys ever used generated on Debian for a couple years. This actually was most well known for SSH, but actually broke all consumers of OpenSSL. And so that meant other things were also affected, like TLS key generation and other stuff. Then there was the dual EC DRBG. So I'll take a little talk about it. Even though RNG is random number generation, there are quite a few different terms. The other one that is often used in government circles is DRBG, deterministic random bit generator. You'll also hear things like PRNG, which means pseudo random number generator. And then there's also what is CSPRNG, which is cryptographically secure. PRNG, pseudo random number generator. I will mostly be using deterministic random bit generator, even though our title is RNG. So in the case of the dual EC, this was proposed as a random deterministic DRBG a number of years ago by NIST. Very shortly after it was proposed, the academics basically said, look, if we don't know how the points were chosen, it is very likely to be backdoored. Turns out, with recent leaks and other information, it turns out that the NSA actually had made a payment to RSA for about 15 million, if I remember correctly, to make dual EC DRBG as a default and be safe. And then as of, a year or two ago?
It was a year ago.
Yeah, just over a year ago. The Juniper was leaked that they actually were using the dual EC also, and that on top of it, they were hacked, this information was leaked, and as part of the hack, the constants for dual EC were changed by some unknown party with no clue why they were changed or other stuff. So it's likely be backdoored, but there is no actual smoking gun because nobody's actually ever turned up one of the private keys to actually leak them. But it's been very well proven that if you generate your own magic parameters for it, that you will actually be able to predict the values of the RNG, and also from that be able to backtrack to what it was. Then there's also another case recently where some researchers queried all the internet to figure out exactly, figure out all the TLS keys that are on the internet. They collected about 46 million different keys, and then they basically set about trying to figure out if there were any related keys. So RSA is a multiplication of two primes P and Q. P and Q are actually your private key. If they ever leak, your key is now compromised. Turns out that there's also a really nasty property about RSA where if P is ever shared, if any of the primes are ever shared between two keys, you can actually very easily factor and discover what the other ones are. So the P and Q must never be related at all to any other key on the internet. Turns out, if you have a bad RNG, your P may be the same, but your Q may be different. You may look like you have a different key, but with very simple math, you're actually able to figure out your private key, and that can also leak. So there are real-world implications behind having a bad RNG. The other case, there are symmetric key algorithms. There are various requirements that if the nonce is reused, you can actually figure out differences between the message. And so it may not seem very much, but if you have two messages that you know the general construct of one, but not the other, the differences can leak very bad information. Also, RSA padding must also be random, otherwise, and you can actually leak signing and information and other stuff. Dean?
Yep. So how we got started looking into this, about a year ago I was doing some FIPS consulting with a well-known provider of FreeBSD-based storage appliances on a kernel cryptographic module that they could get a FIPS validation on. And so one of the questions that came up during the course of this was, well, how do we measure the entropy that's being fed in order to do the entropy analysis requirement of the validation phase? So I started looking into how do I collect raw, unwhitened entropy that's being fed into dev-random for FreeBSD. I was discussing with a former colleague of mine, Sean Webb. Many of you know he knew both of us and said, hey, you're both interested in this system, so why don't you get together? And since John Mark had done previous work in the RNGs and FreeBSD, we decided that rather than just solving my question of how do I get the entropy out, we would get together and just do a full-on audit of dev-random and the RNGs in the FreeBSD kernel.
So as I mentioned previously, RNG is the foundation of cryptography. If you do not actually have a very good RNG, it doesn't matter how awesome your cryptographic algorithms are, everything will be broken. So it's very necessary to make sure that this is a foundational block that is well understood. So the other question is, what exactly is an RNG? I mean, there's noise and other stuff around us. So normally TRNGs, the question, which is also known as a true random number generator or one that is not actually deterministic, as I mentioned earlier, the question is why don't we use them? Computers, they're deterministic. They do not normally have the ability to be completely random. If the computer suddenly decided that 1 + 1 is 3, you'd actually be very unhappy with your computer. Unless it was your bank account, then you'd be very happy. So one of the problems with TRNGs is that they are often very slow, usually measured in megabits. If you're doing IPsec traffic or some other things, very often you'll need multiple megabytes per second in order to satisfy yourself. So using a true RNG is not always possible. There's a number of different methods for collecting real true random thing. There's reverse bias diodes. The one that Intel is using for RD random is the metastate transition of transistors. I won't go into that. We're not needing a down silicon layer lesson. Also, you can also use things like thermal noise or the very low, the analog digital converter on your microphone actually has a little bit of noise at the very low end that is very hard to predict, but it is also vulnerable to side channel attacks. And also the classic other one is lava lamps. Cloudflare has a big wall of lava lamps in their office that they actually use for generation, and there's also a lava lamp that's been used generating RNG on the internet since at least 97, if not 96 or earlier. 96? So yeah, so because you cannot use a TRNG to satisfy your other stuff, you need to actually use a TRNG or other true source of randomness in order to seed what is called a pseudo-random number generator. A pseudo-random number generator takes a small seed of information, usually at least 256 bits. Different random numbers generators will be used different thing. But one of the key components of the pseudo-random number generator, even though it's predictable, if you have 256-bit seed, you will theoretically be able to generate randomness till the heat death of the universe and still not be able to be predicted. That's one of the big key components of having a good RNG. So the question is how does FreeBSD get its randomness? The very first time you install FreeBSD, you're probably going through bsdinstall. I won't talk too much about VMs and other installations. When we actually publish the paper, we can go over that. But the thing is that one of the entropy sources that we use is the keyboard. So when you're pushing enter and other stuff, the BSD installer, FreeBSD itself, is collecting some of the entropy to understand and save it for later. This is basically in FreeBSD 10. We recently added boot time entropy, and I'll talk a little bit more about that. And so the BSD install scripts. Now, the next thing is when you actually start up your system after you've completed the installation, you have to actually have the entropy very, very early on. If you don't, previously back long time ago, there was very little things about security. Things like PIDs were not randomized. TCP IDs were not as actually unique, and people did not realize just how important making sure that they were sequence numbers were not predictable and other stuff, because bad things can happen that way. So we, as things have gone, we've needed to move the ability to initialize the FreeBSD PRNG earlier in the system. And so one of the things that was added in 10.0 was the ability to have the bootloader, known as loader, load an additional entropy file at, early on, so that when the kernel is initializing, even before any disk devices have been probed or attached, we can seed the PRNG, internal PRNG for FreeBSD, and actually get information. And so this was actually a huge improvement. OpenBSD was one of the earlier people, and Theo did a presentation a number of years ago about that. So the boot time loading is actually very good. They zeroed out in memory to help ensure that the seed is not able to be used. One of the difficulties, though, of storing your seed files on disk is actually making sure that once you've used the seed file, no people can actually observe that seed file in the future, because if they're able to observe the seed file, they can now predict the future values of your RNG, and then you have problems with stuff that I talked about earlier. So on the UFS, this is usually not so bad, because the disk block gets overwritten, and then unless you have snapshots enabled or whatever, but even modern disks with even spinning rust and SSDs, even if you overwrite the block on the thing, you may not be able to see the data directly on the disk, but there is a paper that was presented a few years ago that they actually overwrote data on an SSD, then they actually desoldered the flash chips off the SSD, bred them back, and then was able to show that, yes, your data was still readable on the actual physical disk. So there's huge Encryption can obviously help this, but you do have to realize that even though you think your data may go away, it will actually persist on disk for longer than you actually think it will be. ZFS makes this even more complicated because of the fact that ZFS is a copy on write file system. This means that when you overwrite the entropy file, it will not actually write to the same disk block like UFS, and who knows how long it will be before it gets overwritten and other stuff. Trim may delete it, but then your disk may actually not do anything special. So the other thing is RC time loading. At boot, this is what has been traditionally going on for FreeBSD for a very long time, and the RC scripts use some directories to load this. So there's a defense in depth in making sure that the PRNG is well seeded, lots of different sources get that. The other thing that RC time loading allows it to do is to set the mask of what entropy sources are allowed. This was primarily done because some of the entropy sources can be very time consuming, and I'll talk about that in a second. And then also the random RC script is not a random script. The random script is responsible for making sure that entropy seeds are written at shutdown. So the other key part is one of the things that FreeBSD does is it collects entropy as the system is running. And there are a number of different sources that are very useful. As I mentioned, the keyboard, we use timings and actually the keys on the keyboard. So predicting when the clock on the computer detects that your finger actually made the contacts on the key, that is extremely hard because it's sub-microsecond. And so being able to predict that even with audio or other stuff will be very difficult to predict. Then there's other things like mouse, net ether. As we mentioned, masking off, right now there's a discussion ongoing about how net ether is actually having a significant performance impact on the forwarding path, to the point where disabling the net ether RNG harvesting gets like a 30% performance boost. So we're actually looking on that and improving things. So there can be, innocent changes can actually have wide-reaching performance impacts and stuff. So there's a number. The other big one is the interrupt source, and this is actually turned on for pretty much all the disk devices, and this is just really was more effective back in the spinning rest era, where it was timing, basically the timing of the seek to find the disk sector and other stuff. So there are a couple sources that are turned off by default. Those are FSA time and UMA. FSA time basically uses the access time of the file system, and also the UMA was using the slab allocator to actually do randomness. Both of those have a pretty significant performance impact just because of the how much data goes through. So the other key part is once you've collected the data, how do you actually feed it to the RNG system? There's currently 3 different methods used. There's random harvest direct, which is primarily used just for the attach method very early on boot, where you want to actually get the data into the PRNG as quickly as possible. There's harvest fast, which is supposed to be fast for the things like UMA, but even with its being fast, it's still not fast enough to not be noticeable. And then the other one is the general one, which is harvest queue, where it's just effectively a ring buffer that people mix together, that puts in an event, and then there's actually another thread that pulls the data off the ring buffer and then mixes it into that. And so that's pretty much what all the other sources are thinking. So, whoops, wrong way. So as I mentioned, you have to collect, once you collect all this entropy, the next question is what do you do with it? You have different sources, and now you need to actually mix them together in order to make the correct seed for your PRNG. FreeBSD traditionally has used Yarrow. It was introduced, I think it was in 2000. The Yarrow was originally designed by Bruce Schneier, John Kelsey, and Niels Ferguson. Bruce Schneier has done a lot of different, interesting research in this. It used a slow and fast accumulator pool. One of the reasons of using pools is the ability to actually interleave your entropy such that you don't actually that it's harder to predict, so that even if somebody's observing the system, people who don't know what the state of this slow entropy pool is if they haven't been observing for the entire time. And so it uses the SHA-256 hash function. Now, hash function is one of the key the requirements for a hash function is that the data is mixed in such a way that once you see the output, you cannot be able to predict the input. It is very useful also very useful for compressing a very long string and ensuring that all of the entropy, all of the uncertainty throughout the entire string is contained into a smaller value. And so one of the other DRBGs that NIST actually recommends is an HMAC hash-based one, which is also a very good one besides.
So there's a hash and an HMAC.
Yeah. But the HMAC uses a hash, so
yes.
yeah. And so in the case when Yarrow requests data, all the pools are collected, whether it's fast or slow, depending upon the state, and then it uses AES mode to further whiten the noise and also stretch that entropy out for a long time. Recently, we just imported Fortuna into FreeBSD. This is actually a much better design. It is now the default in 11.0. This had similar designers, Bruce Schneier and Niels Ferguson, but this time it had another Japanese, Tadayoshi Kahono. I'm probably mispronouncing the last name. So, and this one they did more effort realizing that RNGs was a much stronger thing. So they stretched out the pools. Instead of having two, a slow and a fast pool, they now actually have 32 pools, which helps guarantee that even a year or two later, there is still entropy that you were collecting from a year or two ago that will be mixed in. And so unless the attacker was observing the entire system for the entire thing, it will be very difficult for them to be able to predict. And again, they use a SHA-256 for the hashing and AES counter mode for the other. So that is the primary source of some of the devices, but for most of the kernel, they use arc4 random, which is now going to be so they used arc4 random, and it was originally imported back in '99. Recently, ChaCha was imported as a replacement for arc4 random because RC4 as an algorithm has been known to have various certain biases and other weaknesses, and it's been suspect but not ever truly thing. But ChaCha20 has a much stronger track record behind it and other stuff. So one of the difficulties, even though modern processors do have some AES-like native instructions, part of the problem is using AES-like instructions in the kernel is not good because by default, the FPU registers are not saved, and they are very expensive to save due to their size and the frequency of context switching. And so the kernel by default does not actually save those. So even though it would be nice to be able to use the AES-like instructions for this, for performance reasons, they're not used. And so that excludes that. So there are also a couple device nodes that are used, dev random and dev u random. And so it turns out that, what was it, back in, when Yarrow was added in 2000, Mark Murray originally did not include urandom and only included devrandom in the port. But of course, the problem was that that broke a number of programs. So he added it back with the intention of deprecating urandom. But I don't think urandom's ever going to go away now. It's just too many pieces of software expected to be used. This actually, the devices, when you read them, actually take the direct output from the mixers, being at Yarrow or Fortuna, whichever one's the default. And it also, the way that the RC script feeds data in, they feed it in through writing to these device nodes in order to provide mixing and other stuff. All right, so hopefully I didn't bore you too much with how the internals are working, but now we'll actually let Dean talk about his analysis.
Thank you. So one of the things that I started in was I needed to analyze the entropy. Part of an entropy analysis report is you have to measure the raw non-whitened entropy, describe your noise sources, describe any mixing and whitening that you're going to go through. So as John Mark just talked about, all of our mixing and whitening, a number of the noise sources that we collect, what's the mathematical measurement of the goodness of the random that comes in from those sources? For appliance vendors, if any of you work for appliance vendors or a company looking to do government sales, the first step towards getting into evaluation for Common Criteria or FIPS is to do that EAR. So hopefully if you haven't already started that but you're thinking about it in your organization, this will give you a shortcut to how to get over that first hump. The NIST provides a standard publication, SP 800-90B, which describes the method for collecting and analyzing entropy from your noise sources that feed into typically your SP 800-90A compliant DRBG. In our case of a general purpose OS and FreeBSD not having a 90A compliant DRBG, we're feeding into Fortuna. But we still need to do the 90B collection and measurement. There are two tracks for measuring that. One is for noise sources which are independent and identically distributed, and this would be, for instance, if you have an appliance with two physical noise sources, diodes you're doing avalanche or something on, and the state of one doesn't affect the state of the other, and you sample from them one bit from the left, one bit from the right, one left, right, left, right, left, right, and mix that together additively. The other is non-IID, and the environmental noise sources in FreeBSD are non-independent and identically distributed. There's relationships between, for instance, when a network packet comes in and when a software interrupt or hardware interrupt fires for the process, so non-independent sources. There are a number of mathematical tests that are specified in the publication for analyzing it. Some of these are more obvious than others as to what they do. Most common value estimate, that's going to be for n number of bytes, which you have to collect 1 million symbols in your word size of your noise source. So 1 million bytes, essentially. What's the measurement of how often bytes repeat themselves inside that sequence of that sample? Compression estimate, obviously, if something is highly entropic, then you can't compress it very small. If you can get a good compression rate, then you have a bad value for your randomness there. So in order to collect non-whitened entropy, and what I mean by whitened entropy is anything that's been fed through a cryptographic algorithm to increase the statistical randomness. So SHA-256 is a cryptographic algorithm. It'll increase the statistical randomness. AES increases the statistical randomness. How Fortuna works, right? We take events, we SHA them, store the value of the SHA, then when we want random, we pull from the pool and run it through counter mode AES. So we have 2 steps of whitening, which is good there. But I needed to figure out, how do I do that? Random dev hash iterate is the last place where events can be observed prior to being hashed. So that's where I needed to pull the entropy from. You can do this two ways. Patch the kernel, just dump it someplace. Or I started using dtrace to do this. Then, as George was mentioning, I then had to actually parse it with Perl and some awk. So all the nasty things, some of the things you're working on would have made this much easier for me. So I used dtrace to collect runtime entropy. I ended up, in the course of this, doing the kernel patch so that I could view early boot entropy also before I was able to access the system to run my dtrace probe to collect during runtime. So basically, I collected the dtrace output of a trace mem for the object being passed in a random dev hash iterate, then took a Perl script to parse that to pull the ASCII bytes from the hex dump, create a binary file, and then run it through the NIST tool. They provide a Python tool that was originally developed by the New Zealand Signals Directorate, Signals Intelligence Directorate, and I've heard talks that when the tool first came over to the U.S., it was by courier in a diplomatic pouch because it was like secret stuff. This was like 10 years ago before 9DB was in publication. Now it's on GitHub, so you can grab it and use it. It's the same one that if you're doing an evaluation for your your clients at work or something, this is the tool that the lab's going to run on the sample they want you to collect. So you can run it yourself and adjust your mixing accordingly. It runs through all the tests, provides a minimum entropy value for each test, and then at the bottom line of the thing, the min-entropy estimate is the worst case value from all the tests, and this is the value that that the Information Assurance Directorate at NSA, who does the EAR review, is going to look at, and that's the one that they're going to base their determination of whether or not you have sufficient entropy feeding into your DRBG. Typically, what they want to see is a min-entropy of around 4 to 6. Below 4, then depending on circumstances and if you do oversampling, et cetera, you can negotiate that it really isn't as bad as it looks. Over 6, I've had that kicked back to me when I worked at SourceFire doing a common criteria. They thought we must have sampled wrong because our min-entropy was so high. Really, I just had a TPM feeding in true random and blasted the crap out of it at 40 gigs with a breaking point. So, I really had that much. So evaluating a control sample. This is what the test looks like when you run it. There's a TrueRand 8-bit control file that comes with it, so you can run as a baseline for your tool. You'll see like the top here, most common value estimate, the first one that gets printed, everybody looks and goes, oh, my entropy is great, 7.8 bits per byte. That's highly entropic. Multiple tests come down. You get about 5.78, so a little under 6 bit per byte from a 1 million samples from a true random number generator, a hardware noise source. I don't know exactly off the top of my head which one they use to pull the sample, but that's an example of, in the best case of true random, not from a pseudo-random number generator, you're looking like about 5.7, and that's what the government will base its judgment on when they're reviewing this. Now here's a sample from FreeBSD. You see where I was pulling, our MCV was 1.98. That ain't particularly good, right? The min entropy, 0.179, less than a quarter bit per byte when I was sampling. That is highly concerning, or at least a little grim. Why? So I took several measurements, both in virtual and bare metal, on Xeon Ni7 with RDRAND and AES-NI, which wouldn't have affected this anyway. was building ports, doing SSH, anything I could think of to try to like drain the pool, make things happen, collect the entropy. I never got a min entropy of even 1 bit per byte. Why? So the raw data contains a lot of that gets fed in and hashed, and that's what I have to look at. Contains a lot of repeat values, null bytes, and predictable values, unfortunately. The best source of high value entropy that I had available to me is read random on the Intel. However, it wasn't being mixed in. On the plane out here, after thinking, am I doing dtrace wrong? So that's why I patched the kernel, and like I still don't see the inputs from read random. John Mark and I actually found that there is a bug that has prevented read random from being mixed in for at least like 2 years. So if you think you were getting it, you were not. That's been reported and should be fixed soon. Mixers, we use the SHA-256 hash on that data. So that makes it, in practical terms, less of an issue. Right? Then what will make us all feel better is that Linux isn't really any better. They, for their own paranoid reasons, don't use RDRAND at all as an entropy source. They expose it as a device node that you can read from user land and then feed back in if you want. Linux-based appliance vendors that I've worked with, this is one of the methods that we have to do in order to meet the requirements. Other things that they have available to fix, Stefan Mueller's done a lot of work. He is from chronox.de. He's an analyst at AtSec, has a jitter RNG patch that really does boost the measurable entropy being fed into dev random on Linux when you run these tests. It is of suspect value for other reasons, but you can pass the test if you turn off everything and use that. HavHD or RNG tools, which provides an RNGD, which will read from a device node that provides some randomness that's not being used as a seed, then writes it into dev random. Unfortunately, that being BSD or GPL2 licensed, I've actually, while I've been here, written a BSD licensed version of the daemon that we can use to feed from, say, a TPM or a USB attached random number generator and feed into to dev random to boost those numbers and provide an additional true noise source in addition to RDRAND once it's fixed, plus the environmental entropy that gets fed in. Now, I mentioned there are a lot of repeat values and predictable bytes. What's getting hashed? And this is a snip taken from a dtrace trace mem probe of what's being fed into random dev hash iterate. So you see here, and I'll start from the right. This hex 08 indicates that this is from software interrupt entropy source. This column E here, this is the Fortuna pool that it's being fed into. This D is a bit flag that for each source, this is always set the same. So this is always the same. This column C here, 04, says I have a size of 4 bytes of entropy in my event. So what was collected was 4 bytes of entropy into an element in the struct that was 2 uint32s, so my second one is all zeros. Then the first 32 bits here is the result of get cycle count, which gets added in as a sort of a jitter source. But the result of this is when you measure it in an unweighted fashion is that 7 bytes are always the same out of 16, and many of the others are counters. And so they're predictable in a linear wraparound fashion. But to conclude, the min-entropy of the data that when we measured with government standards is lacking, but we take a high volume of it. Part of that is what's affecting the performance on the network stack, grabbing mbuff that doesn't have a whole lot of data that's unique. When you detrace from random harvest queue and take a trace mem of like the 240 bytes that get pushed in from the mbuff, half of it's zeros. And then part of it's like MAC addresses that never change. So predictable things. Then it gets a Jenkins hash, which is a linear hash not cryptographically secure, to squash it down to a maximum of 64 bits, the two words in that struct, then append the other stuff, then SHA it, stick it in the pool. But because of the two steps of whitening, and I'll show, I think we removed the slide where I showed the measurement of the output of dev random gets a min entropy of about 5.5. The MCV is like 7.8. It measures close to the value of the true entropy sample file provided by NIST when you read from dev random. The DRBG, in this case, Fortuna, designed by Schneier and his compatriots there, is a very strong design. Can deal with a large amount of low min entropy data and handle it in such a way that the practical effect in the general case is still pretty good. Some of the things that we've been talking about, John Mark and I, potentially to prevent attacks, add a quota system that limits the rate at which a user can request data so that you don't drain the pool too fast. Possibly adjust what's actually getting fed in for hash, because if you're hashing stuff that never changes, you're wasting CPU cycles, including it in the hash, and getting no additional security out of it. To help, then we've also found a number of places where the code just needs to be cleaned up. There's some questionable practices there. We found at least the one bug that kept RD-RAND from being mixed in, which heavily affects the measurement values. With RD-RAND mixed in, I can get a min entropy of about 2 with the other stuff. If I change my harvest mask and I'm only pulling RD-RAND, then it's amazing, but RD-RAND's the result of a counter mode AES DRBG. So it's already been, when you read it, it's already been cryptographically whitened. And some other improvements could be made to seeding. We're still working on that research, and it'll hopefully, when we publish the paper, we'll have those recommendations and those findings there. Did you want to add anything?
Yeah, basically the seeding, one of the issues is that if you seed and then reboot very quickly, there's a risk that you'll actually dilute your entropy because of the way it's both seeded and fed back. And so we're currently evaluating on how to improve that. With how strong things are and other stuff, this does not provide a practical attack or anything. So yeah.
Then Q&A. If you want to see my crappy dtrace probes and my Perl scripts to parse their output and how I got the data, I've got it on my GitHub here. NIST, US NIST Gov SP800-90B _ Entropy Assessment is the Perl script that does the math to get those results for the EAR submissions, and then under development still, mostly complete in terms of the daemon, but I need to add all the other like continuous RNG tests and things that the Linux version has without copying their code and polluting mine, is at my GitHub at bsdrngd. And if you, I can show you it in action with my little TRNG Pro if you're interested, that little box I've been plugging in around here lately. So it's open for questions. That's it. Michael?
Yes, Michael? So, do you want to take that?
Sure. So I thought I mentioned it. I might have glossed over it. I'm sorry, again, with the conversation we had this morning of we work in this all the time, so it's just one of our words. Whitening refers, so you apply a cryptographic algorithm to increase the statistical randomness, right? So SHA-256 is a cryptographically secure hash. If you pass something in, you will get a fixed length string of a uniform distribution of randomness in the bits. We store that, then we use counter mode AES when we pull it out. Counter AES, another cryptographic algorithm, and implementing using the ECB primitive with counter logic around it. another cryptograph, so that increases the statistical randomness. It's seeded with bytes from the stored SHA, and then produces the string of bytes requested.
So, well, one way to think about whitening is that if you have a password like password or some English text, from a computer's point of view, all the bytes values are all restricted into a certain range of the ASCII set. And so from a computer's point of view, they are not very random. The whitening step is a way to basically ensure that the bits are now redistributed throughout the rest of the bytes, and often will be compressed down because of the fact that like English text already has a reduced character set. So you need longer English text in order to create a smaller set of binary randomness. Correct, yes.
Yes.
So the thing, it comes from the thing about making it closer to white noise, because white noise is a very standard, completely random noise that like you turn your radio to a station that isn't thing, that hiss in the background is white noise, effectively.
Over here.
White noise is typically defined as something out of the spectral distribution of 3 dB per octave for your bandwidth.
Yeah.
There's a radio frequency definition for white noise.
Yeah.
It shouldn't be predictable via spectrum analysis.
Yeah. So,
Yep.
a quick short. It's an RF definition, but it should not be able to be predicted throughout the spectrum of whatever your spectrum you're measuring. So, all right. Any other questions?
In the back.
Yeah.
Originally, I think your initial goal was to do for FIPS certification for a hardware product.
Yeah, so I was working at a Common Criteria and FIPS lab as a lead security engineer there. I was doing consulting with a BSD-based storage vendor that isn't sponsoring this conference, and on a kernel crypto module for their for them to FIPS validate this module. In order to go into evaluation for either Common Criteria or FIPS, the first thing you do is you do an entropy analysis report. You sample non-whitened noise that's being fed into your DRBG. Typically, what they really want nowadays when people are building something on commodity hardware and software like FreeBSD or Linux, you sample what goes into dev random. Your SP800-90A compliant DRBG in your crypto module is going to be seeded with the output of dev random, but you have to analyze the input to dev random. You do the math, collect the sample, run the math tools, write a report describing the noise sources you're collecting from, how they work, why you think they're good. NSA reviews this, if they either agree or disagree, and then you can have arguments all you want eventually. I mean, if you don't come to an agreement that yes, your randomness is good enough, then they won't allow you to proceed into evaluation. So since being in evaluation is oftentimes enough for a vendor to get in front of sales and government, that's a major step, a major hurdle they have to overcome. So knowing how to do it right and engineer the system in such a way that you're optimizing the amount of randomness you're bringing into your DRBG is important. That's why, if John Mark said, if you have bad seed into a deterministic number, you have bad output that's predictable or at least weakened, and the strength of your entire crypto system is diminished. So.
Was the assessment successful then, or based on the limitations that you described, did they have to do?
So this I did not in the context. The measurements I took weren't in the context of their system, but typically hardware vendors will oftentimes disable whatever came with, say, Linux, and then put in a chip that they know and can describe, and that's the sole source of entropy. There may be multiple of them depending, because you usually don't want to rely on like one literal sole source of entropy, because if it fails, then you have none. Right. So in the appliance world, they're more, it's easier to get to a min entropy of 4 because you can completely control the system. In the general purpose OS on commodity hardware case, it's going to be difficult. So
right.
did you have a question?
Well, you can grab me later.
Okay.
All right.
All right, that's it.
Please give John Mark and Dean a hand.
Thank you.
Thank you.